Good morning, students. Welcome to the class on organometallic chemistry. Now we will discuss organolithium reagents. What are organolithium reagents? An alkyl group bonded to lithium. Alkyl group bonded to lithium are called as organolithium reagents. This is called methyl lithium, ethyl lithium, N-butyl lithium, secondary butyl lithium, tertiary butyl lithium, phenyl lithium, vinyl lithium. You write the nomenclature for all these lithium reagents. It is just alkyl lithium, methyl lithium, ethyl lithium, N-butyl lithium, secondary butyl lithium, tertiary butyl lithium, phenyl lithium, vinyl lithium. All these organolithium reagents, these are powerful nucleophiles as well as strong bases. The reactivities of organolithium reagents are similar to Grignard reagents, but compared to Grignard reagents, these are more strong in nature. That means they are stronger nucleophiles compared to Grignard reagents. Similarly, they are stronger bases compared to Grignard reagents. Ethyl lithium was discovered by Schlenk and Holz in 1970. Now we will look at the preparation of these reagents. Alkyl lithium reagents are also prepared in a similar fashion like Grignard reagents. So what we will do, we will take corresponding alkyl halide and then we will add lithium wire. In this case, we will add lithium wire. Generally, we use pentane or hexane solvent, and we apply either neon or helium atmosphere. So the product is N-butyl lithium plus lithium chloride. Generally, the percentage will be more than 90%. How this conversion will occur? Of course, I don't need to give you the complete mechanism. I hope so. Lithium is an electropositive element, so immediately it gives out an electron. N-butyl chloride is a good leaving group, so Cl minus N-butyl plus. When one lithium gives one electron, N-butyl cation becomes N-butyl radical, neutral. So Cl minus lithium plus, that gives lithium chloride. Then again one more lithium will give one more electron. So then N-butyl becomes minus, N-butyl minus lithium plus. So the preparation is similar to Grignard reagents, but here the difference is we apply either neon or helium atmosphere. In case of Grignard reagent, we can use nitrogen atmosphere for neutral conditions, but here we cannot use nitrogen atmosphere. Why can't we use nitrogen atmosphere here? So the possible side reactions are nitrogen can react with lithium metal to generate lithium nitride. Lithium nitrates are very stable compounds, so they cannot involve in alkyl lithium reagents generation. So that is why we cannot use nitrogen here. Please take the notes. So lithium immediately reacts with nitrogen to give lithium nitrate, a stable compound. So that will dampen the reaction condition. So we cannot get n-butyl lithium if we use nitrogen atmosphere. So that is why generally we apply either neon or helium atmosphere in the preparation of alkyl lithium reagents. Generally, whenever we want to prepare alkyl lithium reagents, bromine is the best as a halogen. So when bromine is there, alkyl lithium reagents can be easily prepared. When we want to have phenyl lithium, take phenyl bromobenzene, add lithium metal. So we will get phenyl lithium plus lithium bromide. So whenever we want to have alkyl lithium reagents, it is better to use bromoalkanes so that alkyl lithium reagents can be easily prepared. Now, the phenyl lithium, methyl lithium, and vinyl lithium, they are generally insoluble in hydrocarbon solvents. They are generally insoluble in hydrocarbon solvents. So that is why we use ether in case of these reagents. So when I am preparing phenyl lithium, I used ether as the solvent. Okay. Also, n-butyl lithium, secondary butyl lithium, and tertiary butyl lithium react with ether and THF at room temperature. So, whenever we want to prepare these reagents or whenever we want to use these reagents, and if you want to use ether or THF as the solvent, we must maintain very low temperatures. Why? At room temperature or more than room temperature, these reagents will react with either ether or THF. They'll pick up a proton or they'll act as a nucleophiles. So in order to avoid such side reactions, generally we apply low temperatures when we are using ether or THF as the solvent. When we want to prepare allyl lithium, benzyl lithium, and propargyl lithium, when we try like this, then there will be no reaction. So we cannot get allyl lithium, benzyl lithium, and propargyl lithium. No alkyl lithium reagents will be generated here. Why we can't generate allyl lithium or benzyl lithium or propargyl lithium? Because there are some side reactions. Do you remember Wood's reaction? What is Wood's reaction? Dimerization of an alkyl halide in presence of sodium. Similarly, sodium, lithium and sodium both belongs to the same group. So whenever we use allyl halides or benzyl halides or propyl halides, propargyl halides, in the first instance, they will generate the corresponding alkyl lithium But in the second case, they will undergo dimerization. They will undergo dimerization. So that is what is called Wood's reaction. So that is why we generally don't prepare allyl, benzyl or propargyl alkyl lithium reagents in this fashion. When we compare tertiary butyl lithium, secondary butyl lithium and n-butyl lithium, the nucleophilicity of basic nature generally is more for tertiary butyl lithium. Either basicity or reactivity, nucleophilicity is more for tertiary butyl lithium, whereas when we look at the stability is opposite case. Of course, we know if it is more stable, its reactivity is less. If it is less stable, its reactivity is more. Okay. So among these butyl lithium reagents, tertiary butyl lithium is more basic in nature as well as more nucleophilic in nature. Methyl lithium in ether or in THF or in solid state, generally it exists as tetrameric. So its structure is tetrameric in either THF or solid state. Ethyl lithium in solid state, it is tetra